So hello everyone, I'm Cosimo, and today I present a joint work between Johanna Jøsang and Anozaki. The title of the presentation is Extracting Horn Theories with Queries and Counterexamples, because in this work we wanted to extract horn rules encoded in black box machine learning models like neural networks, especially neural networks because we extracted these rules in neural networks because are successful in many domains like game playing, pattern recognition, natural language processing, medicine, finance, and criminal justice. In particular, in those domains on the right, machine learning models are used to give suggestions that affect substantially human life. And when something goes wrong, we would like to know why, or even more, we would like to check the quality of these models before they are used. So in this work, we assume that we have a trained neural network model, and our goal is to extract interpretable rules that we can understand. In order to do that, we are going to use an algorithm proposed by Angwin, Frazier, and Pitt. Everything is explained in the paper Learning Conjunctions of Horn Clauses. And this algorithm asks queries, and the outcome, eventually it outputs a horn theory. I would like to fix the notation, fix the syntax of what is a horn rule, and I will briefly give an explanation of how this learning algorithm works, and then I explain how our technique works. So we fix set of variables from v1 to vn, and a horn, we can write three different types of horn rules. The rule that has a conjunction of variables and as antecedent, and a variable as a consequent, or a conjunction of variables as an antecedent and a special symbol bottom as a consequent. The last type of rule is in which we have antecedent top, special symbol top, and a variable in the consequent. We give meaning to these formulas by means of an interpretation that are a subset of the set of variables, and the interpretation can satisfy a rule or not. If it satisfies if both the antecedent and the consequence are subset of this interpretation, or the antecedent is not a subset of this interpretation. Intuitively, this says that a rule is satisfied by an interpretation if the antecedent is set to true, and then this means that also the consequence must be set to true. This other type of rule says that in any case, the antecedent of this rule must be set to true, and this type of rule constrains the model to have these variables on the head, on the consequent, always set to true. For example, assume we have this horn theory. This interpretation does not satisfy the horn theory because of this first rule. Variable 1 and 2 are set to true, but variable 3 is set to false. On the other hand, this other interpretation satisfies the horn theory because this rule is trivially satisfied because the antecedent is not satisfied. Also in this case, in this rule, the antecedent is not satisfied. And well, this interpretation satisfies v4 and also v5. We can do a nice feature of this logic is that reasoning is tractable, and of course with reasoning we can do interesting things, like for example, assume we know that the variables 1, 2, 4, and 7 are set to true. According to these rules, we have that if those variables are set to true, then variable 9 must be set to true. For example, this rule says variable v1 and v2 are set to true, then also v3 must be set to true. And with the reasoning, we can identify those rules that are responsible for a logical consequence and search for wrong rules. Okay, I close the parenthesis about why we're interested in learning horn theories. And I'll explain briefly the learning algorithm that the Horn learning algorithm that falls into the place into the exact learning model. In this learning model, we have a learner and a teacher. The learner here the role of the learner is played by the learning algorithm that starts with an empty hypothesis. And the goal of the learner is to identify a hypothesis that is logically equivalent to the target. The learner can ask, in this case, the learning algorithm can ask two types of queries: a membership query, in which the learner selects and sends a interpretation to the target, to the teacher. The teacher checks if this interpretation satisfies the target, and if the interpretation satisfies the target, then the answer of this query is yes. If it doesn't satisfy the target, then the answer is no. And according to the answer of this query, the learner the learner acts accordingly. The second type of query is called an equivalence query. Here the learner sends its entire hypothesis, and the teacher checks if the hypothesis is logically equivalent to the target. If it is not the case, like in this scenario, the teacher will send a counterexample that is an interpretation that satisfies the target but not the hypothesis, or vice versa. Otherwise, if the hypothesis is equivalent to the target, the teacher will tell, yes, they are equivalent, you should stop learning. This learning algorithm, I give you some details about this learning algorithm. This learning algorithm runs in polynomial time with respect to the size of the target and the number of variables, with respect to the number of clauses in the target. And whenever it receives a counterexample that satisfies the target, it removes from its hypothesis those clauses that are falsified by this counterexample. That is an interpretation. Or whenever it receives a counterexample that falsifies the interpretation, the target, then it adds some rules to the hypothesis. Okay, our approach works as follows. We assume that we have a data set of interpretations that are classified, labeled 1 if this interpretation satisfies the unknown target, and 0 if this interpretation does not satisfy the target. Once we have this data set, we train a neural network that has as input layer a number of nodes equal to the number of variables, and the output layer, and it has an arbitrary number of hidden layers with an arbitrary number of nodes. We here in this work, we don't assume any architecture on the neural network. And the neural network has to solve a binary classification problem. Given as input an interpretation, it outputs, for example, 1 if this interpretation satisfies the target, and 0 otherwise. Once we have trained this model, we run the Horn learning algorithm that will ask queries. And we use the predictions made by the neural network to answer those queries. In this way, then, when the learning algorithm terminates, it will output a Horn theory that is, it's supposed to be equivalent to the Horn theory encoded in the neural network. In order to simulate a membership query, when the Horn learning algorithm selects and sends an interpretation, we ask the neural network for the prediction, for the classification of this interpretation, and we return yes as an answer to this query if the interpretation is classified as 1, so if it satisfies the target, or we return no otherwise. In order to simulate, so simulating a membership query is simple, but simulating an equivalence query is less trivial. In order to do that, we are going to exploit the connection between the exact learning model and the probably approximately correct learning model, a PAC learning model. So when it works as follows: when the learner sends its hypothesis, we generate randomly a sample of interpretation, and we ask the neural network for the classification of each of those interpretations. Once we have done that, after that, we search for counterexamples in this sample of classified interpretations. If, for example, an interpretation is labeled as 1, but does not satisfy the hypothesis, then we may send this as counterexample. Or the other type of counterexample is the one that is classified as 0, but satisfies the hypothesis. In literature, there are some results stating that if we have a sample that is big enough, we can give some probabilistic guarantees on the outcome of this hypothesis, of the generated hypothesis. We tested our approach first with a synthetic dataset and then with other datasets. But here I will only talk about this synthetic dataset. We fixed the number of variables, and we generated randomly a target. Then having this target, we generated randomly interpretations, and we labeled the interpretation as 1 if they satisfied this randomly generated target, and 0 otherwise. Once we have this sample of labeled interpretations, we use this dataset to train a neural network model in a case where we do not apply any noise to the labels of the examples in the dataset, or in which we apply then noise of 0.1. This means we have a 10% chance of flipping the labels of this interpretations in this dataset. Once we train the neural network model, as explained, we then run the Horn learning algorithm that will output a Horn theory. So in these tests, we set the maximum number of equivalence queries that the learning algorithm was allowed to ask to 100. After that, once we had the hypothesis, then we computed all the possible combinations of interpretations that can be formed with the decided number of variables. And we computed the number of interpretations that are labeled differently between the target, the hypothesis, the target and the neural network, the hypothesis and the neural network. For example, this number says that so in the entire truth table of interpretation that are 2 to the power of 8 possible interpretations, only 0.6% of those interpretations were classified differently between the target and the hypothesis. And in all those tests that we made, this number is less than 2%. Yes, so I conclude this first part of the presentation. Now I pass the virtual microphone to Johanna Jøsang that will explain the second part of our tests with another dataset. Thanks for your attention.